If you've ever spent even a little bit of time in a math class, you know the absolute golden rule, right? You cannot divide by zero. It's always presented as this unbreakable law of the universe, honestly, right up there with gravity. But today, we're not just going to accept that rule blindly. We are going on a mathematical journey straight into the dark heart of this undefined operation. We're going to see exactly what happens to physical machines, to algebraic logic, and to modern computers when we literally force them to face mathematical oblivion.
To really wrap our heads around the sheer destructive power of dividing by zero, we need to jump back to a time before digital computers, back when math was physical. Picture a beautifully engineered 1950s mechanical calculator. When someone commands that marvel of brass and gears to divide a number by zero, it doesn't just, pop up a polite little error message. It literally breaks physical reality. The machine goes into this chaotic, terrifying loop of endless motion, gears just spinning violently until you're forced to rip the plug right out of the wall. But why? Section 1. The Infinite Mechanical Loop. Imagine typing this stark, simple equation into one of those old calculators. 20 divided by 0. Now, these machines didn't have the fancy safety checks of modern software. They were designed to follow pure, relentless logic. So, when commanded to solve this, the calculator attempts to do it by subtracting 0 infinitely. It subtracts 0, sees that 20 is still left, and tries again, and again, and again. It creates a horrifying mechanical loop that simply cannot stop. Section 2. What is division really? Let's strip this down to the basics. See, mathematics relies on two fundamental models for division. The first is the partitive model, which is basically just sharing. If you have 12 cookies and you share them equally among 4 friends, everyone gets 3. Super simple. But what if you try to share 12 cookies with 0 friends? How many cookies does each non-existent friend get? The physical act of handing them out can't even begin because there's literally no one there to receive them. It's a completely nonsensical scenario. And then we have the second model, the quotative model, which treats division as repeated subtraction. 10 divided by 2 means we subtract 2 5 times until we hit 0. But look at the loop that happens next. 10 divided by 0 means we subtract 0, and we still have 10. So we do it again and again. This step-by-step logic perfectly matches why those 1950s mechanical gears spun endlessly. You can never, ever exhaust a physical quantity by subtracting nothing from it. Section 3. The algebraic contradiction. In formal mathematics, division actually isn't a standalone operation. It's strictly defined as the exact inverse of multiplication. Think of it like this. If A divided by B equals C, then it must absolutely be true that C multiplied by B equals A. They are two sides of the exact same coin. So what happens when we apply that strict rule to our forbidden operation? Well, if we try to define 1 divided by 0 as some unknown number, let's call it x, then by definition we have to be able to flip it in reverse. We must be able to find a number x that, when multiplied by 0, magically equals 1. And boom, here's the stark impossibility. We know from the basic axioms of arithmetic that absolutely anything multiplied by 0 is 0. There is no magical number x that turns into a 1 when multiplied by nothing. If we allow ourselves to pretend there is, if we allow division by 0 to exist, we are forced to accept that 0 equals 1. And if 0 equals 1, the entire foundational structure of algebra shatters instantly. Which brings us to a really crucial distinction mathematicians make. Dividing a regular non-zero number by 0, like 1 divided by 0, is called undefined because there are 0 solutions. It's a pure contradiction. But look at the other end of the spectrum. 0 divided by 0 is called indeterminate. Why? Because if you ask, what number multiplied by 0 equals 0, the answer is literally every single number. It has infinite solutions. Because it could be anything, we just can't determine a unique value. You know, you've probably seen those famous viral math proofs online that supposedly prove 2 equals 1. Well, the dark secret of those tricks is that they always rely on a fallacy where at some point both sides of an equation are divided by a term like a minus b. But if a equals b, that term is secretly 0. By sneaking a division by 0 into the math, they completely break the laws of logic to get 2 equals 1. It's the perfect illustration of why mathematicians strictly forbid this. Section 4. Histories struggle with 0. Humanity didn't just figure this out overnight. To understand the struggle, we have to look at the birth of zero itself. For thousands of years, zero was just a placeholder, a blank space in a number. But here we have the Bakshali manuscript from India, dating back as far as 300 CE. This is a monumental artifact. It's the oldest written record of zero actually transitioning from an empty space into a functional number that you could do math with. And that brings us to the great Indian mathematician Brahmagupta in 628 CE. He was an absolute pioneer, writing down the very first rules for how to add, subtract, and multiply with this brand new number called zero. But when he got to division, he stumbled. He incorrectly claimed that 0 divided by 0 is just simply 0. Honestly, it was an honest mistake at the very frontier of mathematics.
This specific problem haunted mathematical minds for centuries. Brahmagupta thought it was 0. A couple of hundred years later, Mahavira tried to fix it, but he incorrectly said a number divided by 0 just remains unchanged. Finally, in 1150 CE, Bhaskara II introduced a profound new idea. If dividing by smaller and smaller decimals gives you bigger and bigger numbers, then dividing by 0 must equal an infinite quantity. And this concept of infinity became the accepted answer for hundreds of years. Section 5. The Riemann sphere solution. This pursuit of infinity eventually pushed advanced mathematics to find a radical geometric solution. Welcome to the Riemann sphere. This is where math gets truly cinematic. Instead of a flat, infinite number line that just goes on forever left and right, complex analysis literally bends the entire complex plane, wrapping it up into a sphere. The 0 sits right at the bottom pole, and as numbers grow infinitely large in absolutely any direction, they all stretch upward and converge at the exact top of the sphere. In this incredibly elegant visual model, that single point at the top is called complex infinity. And right here, division by 0 is finally well behaved. The function 1 divided by z evaluates perfectly to complex infinity at the origin. But there is a catch. To gain this godlike ability to divide by 0, mathematicians have to sacrifice standard algebraic properties. You actually lose the ability to do normal arithmetic. It's a beautifully contained system, sure, but it's essentially an alternate reality. Section 6. How modern computers survive. Let's step back from advanced geometry to see how we are containing this void today. The answer lies in how a computer's hardware actually represents numbers. If a program uses basic integer arithmetic and tries to divide by 0, the hardware literally has no binary code to represent the answer. It throws a violent hardware exception, instantly crashing the program to prevent data corruption. But if it uses floating point math, the error is safely contained and the software actually survives. This modern survival is entirely thanks to a mathematical cage built back in 1985 called the IEEE 754 standard. Computer scientists realized they couldn't just let systems completely crash every time 0 showed up as a divisor. So they reserved specific binary patterns. If you divide by 0 today, your processor doesn't spin infinitely like those old gears. It outputs one of these safe digital placeholders like positive infinity, negative infinity, or NaN, which literally stands for not a number. It's brilliant. It allows the math to fail gracefully without taking the whole machine down with it. We started this explainer with mechanical gears spinning wildly out of control, and we've ended up with a digital cage perfectly designed to hold infinity. We've managed to contain the 0 divisor in our modern world, effectively walling off the void so our technology can keep functioning. But it really leaves you wondering, looking out at the dark, expansive universe of abstract logic, how many other fundamental mathematical rules are out there, just waiting to be pushed to their absolute limits? It's definitely something to think about. Thanks for joining me on this explainer, and keep your curiosity sharp.